Okay, so let's go to the class notebook, and I want to finish up clippers and clampers today. So okay, clipper circuits. All right. So for this kind of circuit, these are known as wave shaping circuits. What we are going to do is we have wave shaping circuits. So we have a diode connected in either in series or in parallel to the output. And what it does is it takes the incoming input waveform and modifies it in some way. Thus, we say it's shaping the waveform. Okay, it's shaping the waveform. So we already saw in a rectifier circuit, specifically the half-wave rectifier, where one half cycle is cut off and only one half of the input waveform is transferred to the output. Okay, and that kind of clipping at the from the input to the output is known as a clipper circuit. Okay, so that circuit, the half-wave rectifier, was a series connection, right? The output is connected in series to the diode. This, in this circuit, we are taking the output across the diode, so in parallel to the diode. So we can call it as a parallel clipper circuit. So a half-wave rectifier is also a wave shaping and a diode clipper circuit. Okay. To analyze these kind of circuits, I typically like to use the ideal diode model. Makes it very easy to analyze the circuit without worrying about any calculations or voltage drops or diode currents. So typically we would use the ideal diode model. Okay. And so what we will do is we will apply both positive and the negative half cycles to the circuit, analyze it based on the ideal diode model, and determine what the V out or output is. Right now, we are not combining both DC and AC. We are simply applying an AC waveform. That AC waveform could be a sine wave, a square wave, triangular wave, does not really matter. Okay, does not really matter. But let's say you apply a sine wave input to it. Okay. Positive half cycle, voltage is positive. So the anode of the diode would be higher than the cathode in terms of electric potential. So based on the ideal diode model, what do we replace the diode with? Short circuit, absolutely. So the diode is on, whether it's forward bias, diode is on, we replace with a short circuit. If it's reverse bias, diode is off, we replace with an open circuit. So in the positive half cycle, again, doesn't matter what kind of waveform it is, the diode would behave like a short circuit. And so what is V out or VO? 0 volts, right? 0 volts. Whatever input is coming is going to the resistor, forming a closed loop and going back, right? V out is 0. The exact opposite happens in the negative half cycle. Diode is now reverse bias because you're applying a negative voltage to the diode. We can also represent each individual half as a DC voltage. Even though the value is varying, if we wish for analysis purposes, we can represent it like this. Okay. Just strictly for analysis purposes. I found it helps me. So when I was a student, when I was learning, and even now, when I want to analyze a circuit, I simply, if I'm analyzing for one half, I simply replace it with a battery or a DC voltage. It just helps me to analyze the circuit. So just a small suggestion. So the same thing for the negative half cycle. And of course, the diode is now reverse bias. So it's off. And then whatever V in we give appears at the output. So V out is equal to V in. Right? And so my output, I'm going to draw both the waveforms right below the circuit. This is V in. And let's say we talked about sine wave. So let's stick with sine wave. Positive half cycle is cut off or clipped. So it's completely zero. And then, of course, we have the negative half cycle as it is. This is V out or VO. Positive half cycle is clipped, hence the name clipper circuit, diode clippers. Let's take a pause. Let me know if you have any questions. Make sense? Any questions? Good. Okay, then let's see. Now this is the basic, very basic diode circuit. Okay, now let's see how we can use it. So if we attach a battery to it, now we flip the diode. The direction does not matter. Our analysis approach remains the same. Diode, uh, diode connection is flipped. We have also connected a battery along with the diode. So let's see first. The anode is connected to a 4-volt DC source, meaning the anode is held constantly at 4 volts. Talking about this circuit on the right. Okay. So the anode is held at a constant value of 4 volts. So what does that mean? Is the diode on or is it off? Well, it depends, right? Yeah, absolutely. If the cathode is above 4 volts, the diode is off. If the cathode goes below 4 volts, the diode remains on. So we would say in the positive half cycle, or positive half, with V in or Vi less than 4 volts, the diode is on, so behaves like a short circuit. And if it behaves like a short circuit, then what is V out? What is V out? 4 volts. Absolutely. V out is 4 volts, or if we just label a variable VDC or V battery, we say V out is equal to the battery voltage, right? As soon as the V in starts climbing and goes above 4 volts, cathode is now higher than 4 volts, diode turns off, and if it's off, V out is equal to V in. So still in the positive half, and V in now climbs above 4 volts or the DC value, then the diode turns off. Value of the battery does not matter, and V out or VO is equal to V in. So far, so good. Where? Here? Yeah, it's still the positive half. Yeah, still the positive half. So it's the positive half, and I'll draw a waveform. I'll draw a waveform later once I finish with the negative. But it's straightforward. So now, sorry, I keep using the word straightforward. If it's the negative half cycle, what is the diode state? If it's a negative half cycle, yep, it'd be forward bias. Right? It does not matter. It's a negative half cycle, meaning the cathode is held at a negative potential. 0 going to -1, -2, -3, -4. So it's always going to be forward bias in the negative half cycle. And again, let's draw it out this way. Negative half cycle, minus here, plus here. Diode will always be on. Right? Cathode is always held at the negative potential. So negative half cycle does not matter. The value does not matter. Right? V out will always equal 4 volts. Make sense? Right? I'll draw the waveform. It'll make, hopefully it'll be a little bit more clearer. So let's see here. And this is our input waveform. This is V in. And let's see. This is output. Okay. Now, I don't know what this level is. Don't really care. I'm just hoping, or not hoping, I'm just using it as an example and assuming that it's going to be higher than 4 volts. So let's say 4 volts is here, right? Let's say this is 4 volts. In my waveform, right below 4 volts, diode is on, and so battery is connected, so my output stays at 4 volts. Then the diode turns off, and V in is delivered to the output. Okay. And then at this point, 4 volts, diode turns on again, battery is connected to the output, and I get 4 volts. So positive half cycle, again, when V in is less than 4 volts, let's say this is 4 volts, when V in is less than 4 volts, diode is forward biased, diode is on, battery is connected directly to the output. So my V out is a constant level of 4 volts. Once V in goes above 4, diode turns off, everything is disconnected, the battery is disconnected. V in reaches directly to the output, so V out is equal to V in. And so we get the small cap at the top. Does that make sense? Right, everyone? And then when it goes below 4 volts, again, the same thing happens. In the negative half cycle, diode is always on. So you'd have a completely flat line for the negative half cycle. And this, of course, is 4 volts. Excuse me. All right, questions? Yes. Any questions? Yes. So how come the input doesn't? No, not in this case. Not in this case, not in a simple case. So we have, I think the question being asked is, doesn't the input add anything to the output, right? So no, because the output is being taken directly across the battery. That's why. So the constant flat line. So nothing else would matter in that sense. If it's a capacitor, then it would add on, which actually is the next circuit, the clamper circuit. So that's a very good point. If it was in series with the battery, then yes. But in this case, the AC would simply flow through the resistor through the battery in this way, but the output is taken directly across the battery. So it would still get the same 4 volts. An example of that would be like using our devices while they are being charged. So if you have a battery in our cell phones or tablets or laptops, we connect it to a charger, the entire device is still functioning from the internal battery. So it's the complete circuitry of our device sees only the battery. It doesn't see the charging circuit. It doesn't see the charging circuit, right? If your battery is dead completely and you plug in your device, you still won't be able to use it. Okay. Very early just going on a little bit of a tangent. Very early smartphones, I had a few of those where you could remove the battery. So you could use it like a laptop, even with the battery removed, just plugged it into the charger and it would still work like a laptop without the battery. But now all devices, pretty much the batteries are inside, even if they're removable or not. The entire device circuitry, the boards and everything just simply sees the battery. It does not see the charging circuit at all. So even though you're charging it, the battery still receives a charge, but everything else is only seeing the battery. So a very good point. Did everybody understand the question? Okay, right, that was the answer. All right, so I got 4 minutes left. I want to finish up clamper circuits. Okay, now clampers. So here, what we're going to do is we're going to clamp the level of a AC input waveform to a specific DC voltage. Okay, and this is something that you do when you apply a DC offset in your function generators, right? You generate a waveform with some peak to peak value, and then you apply a DC offset voltage to shift the waveform either up in the positive direction or shift it down in the negative direction, right? So this is one such example. So in the positive half cycle, let's say it looks like this. Diode behaves like a short circuit because the anode is connected to the positive end. V out is equal to 0. However, the capacitor charges through the diode. So you have VC, and this was V in, this would be V in by 2, and VC charges to a level of V in by 2. VC charges to a level of V in by 2. Okay. Let's say we are applying